this video we're going to go over material balance with incomplete combustion. So incomplete combustion is when the fuel burns with limited oxygen. So compounds like carbon dioxide can form in addition to carbon dioxide and water. So we may also need to calculate excess air, which is calculated by subtracting the air supplied minus the theoretical air and dividing that by the theoretical air. So if we get started with the problem, we have fuel and air, and we put them both into a boiler, and we have water in it as a liquid form, and we have flue gas, and we have the composition here. It says determine the composition of the fuel and the percentage excess air. So what we need to do to start is to choose a basis for this material balance equation. So I'm thinking we should start with 100 kilomoles as N5 because we're given the compositions of all of the components, so we'll most likely be able to get somewhere if we form the basis as that. So N5 is 100 kilomoles. So now we know the moles of all the components. So what we can do now is we can use that to get the moles of air, or the theoretical air required, because if you think nitrogen is inert, so it doesn't react, and nitrogen is only supplied in air. There's no nitrogen in the fuel, there's no nitrogen here or anywhere else except from here and here. So we can use this to write a material balance to find the amount of air required, and that'll be N3. So if we do a nitrogen balance, so coming in we have N3 multiplied by 0.78 moles of nitrogen. Because nitrogen is a diatomic molecule and it only exists in this problem as a diatomic molecule, so always N2. I'm going to do the nitrogen molecule material balance. So we would have N3 multiplied by 0.78, and then coming out we have N5, which you know is 100, and that is multiplied by 84.77%. So we know we have 100 multiplied by 0.8477. We can rearrange to get N3, which is 100 multiplied by 0.8477, and that's all divided by 0.78. So that gives us 108.7 kilomoles. This 100 kilomoles, forgot to mention, this is a per hour basis. So we're going to take this whole thing in 1 hour. So we're going to stick with 100 kilomoles of N5, and so we'd need 108.7 kilomoles of air. So now that we have that, we can use this to do an oxygen balance. So if we see here we have O2, but say in water we have O by itself, like oxygen by itself, as one atom, and then we have O2, O. So we're not going to do an oxygen molecule balance, because although oxygen is a diatomic molecule, it can exist by itself in this material balance. So we're just going to do an oxygen by itself material balance. So coming in we have we don't have any oxygen coming in through here, only through air. Now that we know N3, we can calculate the oxygen here. So we have 108.7 kilomoles of air, 22% of that is oxygen, and we have 2 lots of oxygen atoms in each oxygen molecule, which is what makes up 22% of the air. So to take into account both the oxygen atoms, we multiply it by 2. So that's everything coming in. Coming out, so we have an oxygen here. We don't know what N4 is though. So we have N4 multiplied by, and oxygen here is 100% because it's 100% water. So it would just be N4 multiplied by 1. And then we have N5 here. So you have 100. And that's multiplied here, 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 and here. So we have 100. And then that's multiplied by 7.95%. So 0.0795 times 2, because it's CO2. That gives us 0.159. By the way, because they're all part of the flue gas, they all have N5 as 100, so I'm just factorising 100 out and adding it all together. It just makes it a bit shorter so I can fit it on the page. Plus, we take into account carbon monoxide, and we only have one oxygen there. So it's times, and that's 0.45%, so it's 0.0045. Plus we have water here, so that's 0.042, and then we have an oxygen molecule, so that's 0.0263 multiplied by 2. So that gives us 0.0526. So I'll just neaten this up a bit because it looks a bit odd here. So we have 108.7. If we shorten this bit, we multiply everything, we get 47.828, and that equals N4 plus all of this side. So we have 100 multiplied by 0.159 plus 0.0045 plus 0.042 plus 0.0526, and that gives us 25.81. So if we rearrange, we can solve for N4. So 47.828 minus 25.81, that gives us 22.081, and we're working in kilomoles. So now that we have N4, which is the amount of water that's released, we can actually now work out the hydrogen balance, right? So because we have N3 and N5 already, we can work out the hydrogen here, because we know N4, which means we can determine the hydrogens here. We can also do a carbon balance, because we don't know N1, but we know N5, which has got carbon and carbon dioxide and carbon monoxide, and there's no carbon here or here, which means we can now do carbon and hydrogen balances and determine the composition of the fuel. So if we start with a carbon balance, we have here, so we can do if we have here N1 and we only have one carbon, so we have N1 equals, and here we have 100 multiplied by 0.0795, so 100 0.0795, and then we take into account carbon monoxide plus 0.0045, and then we get N1 equals 8.4. kilomoles, of course. So that N1, so the 8.41 kilomoles, that represents the moles of methane, because all the carbon that's released from here comes from the methane, right? On the inputs, that's the only place where the carbon is present, which means we've just worked out 8.4 kilomoles of methane. So now that we've done that, we can make a hydrogen balance, as that's the last one to do. So with the hydrogen balance, we have to take into account this, and the fuel to determine how we're going to do a hydrogen balance. We're going to do hydrogen as a single atom. So coming into the system, we have hydrogen in the fuel only, as there's no hydrogen in the air for this example. So we have N1 multiplied by 4, because we have 4 atoms of hydrogen in methane, and we know N1 is 8.4. So 8.4 times 4. And we also need to take into account this hydrogen. So we have N2 times 2 plus N2 times 2. So that's everything going into the system. Coming out of the system, we have N4 multiplied by 2, and we already calculated N4 before. N4 was 22.018. And for the flue gas, we have N5, which we already know. And for hydrogen, it's only here. So we have 100, which was N5, multiplied by 0.042 multiplied by 2, because we have 2 atoms of hydrogen in that H2O. So if we rearrange everything in terms of N2, we can calculate. So if we have N2, so we have 22.018 multiplied by 2 plus 100 multiplied by 0.042 times 2, and then we minus 8.4 times 4, and then we divide by 2. That gives us 9.418 kilomoles. Now that we've got our kilomoles of hydrogen that was in the fuel, we can determine the composition which we were asked to do. So in terms of hydrogen and methane, we calculated they were 9.418 kilomoles of hydrogen and 8.4 kilomoles of methane. To calculate the composition, you work out, say for hydrogen, 9.418 divided by the total, which is 9.418 plus 8.4. So the hydrogen composition is 52.9%. And of course the methane composition is 47.1%. This is to 1 decimal place. So that's the composition of the fuel. The second part of the question asks you to calculate the percentage excess air. So to do this, we need to go on to the next page and use the equation. So to calculate the percentage excess air, we need to calculate the amount of oxygen that was needed. So we have our fuel, and we calculated we had 8.4 moles of this, and for hydrogen we had 9.418. So 9.418. So to calculate the number of oxygen molecules that we needed in this material balance, we can use the two reactions. as if it was combustion, because this is what it was. So CH4 plus oxygen, and that gives you carbon dioxide plus water. We have hydrogen. Now take into account when you combust hydrogen, you combust it as a single atom. So it's like this. So now we need to balance them, right? Because these don't balance. So we have 1 carbon, 4 hydrogen, 2 oxygen. We have 4 oxygen, so we need to put 2 here. Then for the next one, so we have 2 oxygen here, so we'll need 2 here because we need 2 oxygen on this side. And here we have 4 hydrogen, so put a 4 there. Since we're working on single H's, H by itself will be 9.418 times 2, which gives us 18.836. So now we can calculate the amount of oxygen required, and this would be the theoretical oxygen. So we have 8.4 moles times 2, so that's 16.8, plus, now we have a coefficient of 4 here and a coefficient of 1, so we need to divide this by 4. 18.836 divided by 4, so we have 4.709. If we add them together, we get the theoretical oxygen of 21.509 kilomoles. Now this is our theoretical. The air actually supplied, we calculated on the previous page. So we had air here, we calculated N3, and we know the composition. So N3 is 108.7, and the composition is 78%. So 108.7 times 0.78. This gives us the air supplied. So 84.786. So that will be for nitrogen, and 108.7 times 0.22, which is the oxygen, which is what we need. So we have the theoretical oxygen required, which is 23.914. So this is the... Now using the equation on the previous page, we do the oxygen supplied and that's how we calculate percentage excess oxygen. So oxygen supplied 23.914 minus the theoretical oxygen, which is this, so 21.509, 21.509, multiply by 100 to get percent, so 23.914 minus 21.509 over 21.509, and that gives us 11.2% excess air. And that's it.